Hello, everyone. I wanted to talk about the derivation of the Gibbs free energy um, as as a recorded video. One thing I do want to say about this before we get started, it might be important that you are able to do a derivation of a thermodynamic property. So just kind of pay attention to how we do this and consider how you would apply this to maybe a different situation, so that you, given this kind of information, how would you go about doing that? So we're given this equation. The change in entropy of the universe is equal to the change in entropy of the system plus the change in entropy of the surroundings. We've also shown that the change in entropy of the surroundings is equal to the negative enthalpy change of the reaction divided by the temperature. And so what we want to do, we want to get from this equation to this equation, and then we'll see how we get from this equation then to the Gibbs free energy. So first thing we'll do, we'll start with the kind of given equation. And so I'm just putting, I guess that looks like it says sun. So I'll say UNV for universe, and then SYS for system. And then what I'm going to do for this change in entropy of the surroundings, I'm going to take this value and plug that in there. So we have negative delta H of reaction divided by temperature. And so we have that, and we're looking for this. And so maybe we can look at what can we do to, delta S of universe. We have a negative T with that. Maybe if we multiply through by a negative T, we'll see what we get. So I'm going to say times minus T. Oh, I'm sorry. I should say, yeah, times a, let me start over. Times minus T. Okay, so we'd have negative T times the change of change of entropy of the universe. So that would give us negative T delta S of the universe. And then we'd have T times delta S of the system. I'm sorry, that should be negative T, right? So we're multiplying by a negative T, so negative T times delta S of the system. And then for this last one, we would have, I'm going to maybe do this in a few steps. We would have times negative T times negative delta H of reaction over T. Okay, so what's going to happen here is the T's will cancel and the negatives will cancel. So let's rewrite that. We would have negative T delta S of system plus delta H of reaction. And then over here, this is the same. Negative T delta S of universe. Now, in the long run, we don't care about delta S of universe, and the negative T part multiplying isn't that important. What we're going to do is we're going to define that as the Gibbs free energy. So what that gives us, let me make some space here. We'll just put this over to this on the side here, is delta G is equal to the rest of this. And then we're just going to make a few changes to how we write that. Instead of starting with a negative sign, sometimes if you start with a negative sign, it's easy to kind of lose it along the way. We're going to flip these and have the other one first. So delta H first, and then this one, so minus T delta S. Now, one other thing you might notice I changed there, I did not include system or reaction. And what we're doing here is when we get to this point, we assume everything is about the system. So delta H of reaction is the system, delta S of the system, that's the system. They're about the same thing. So everything is about a change that's happening as the reaction is taking place. So the change in enthalpy of the reaction, change in entropy of the reaction, and then we're relating that to this thing we're calling delta G. And we've derived how we got to that from this equation up here. We've defined delta G as basically being equal to negative T delta S of the universe, and we're never going to really have to use this part again unless it comes up in another derivation. From here on out, this equation, most important equation of the chapter, but at the same time, you want to understand how we went through that derivation, be able to do something similar, perhaps for another thermodynamic value.